so let's get this started here. So I'm covering the second section. As you can see online and up on my board, Salim, Yassine, as you can see, your test date. So you guys have yours next Tuesday, so a week already from today. Yes, I know Group 2 has a whole extra day to study in addition to you guys. Why is that? Well, last test you had an entire weekend before your test. So this is kind of to compensate for that. And then you have spring break, and then your lab test is the day you get back.
What? Oh, we're coming back to a lab test?
Yeah.
The day on?
Yeah. So if you would like to discuss this, I can discuss it later. I'm not going to waste the time of everyone who's on the video because you just spent a bunch of time complaining how they ask a lot of questions, and now they are going to complain about how much you're complaining about this. So it's give and take. Like I said, they have to suffer because of you guys have to suffer because of them. And I'm not editing this out. They can watch this whole thing if they want. So I'm going to start teaching, and you can talk about this stuff later. So, yesterday, brief recap for those of you who were unwise enough not to watch it. We are talking about equilibrium. Equilibrium is basically an extension on dynamics that we did last unit, which is all forces. The nice thing about this is all my forces add up to equal 0. So my net force is 0. That's essentially what we did yesterday. So if you didn't watch it, that's the gist of it. Today, we're going to be talking about a different type of equilibrium. And this involves something called torque. And torque, any of you who are car fanatics, you will understand this term of torque. It has to do with how much your wheels can spin and how much force they can apply at that specific wheel size. So that's what we're going to get into today. So body in translational equilibrium, which is what we talked about yesterday, meaning I can move something up and down, or I can move it left and right at a constant speed, or it's stationary. That's translational equilibrium. Today, we're going to deal with something else. So a body in translational equilibrium will have no acceleration in the x or y directions. However, it can still be rotating. So as I said yesterday, this unit is very important for those of you doing engineering. You will see this a lot. Because if you think about specifically civil engineering, in general, you don't want your buildings to move or accelerate left or right, up or down. So you want your forces to be balanced on a building. Same thing, we don't want a building to rotate, hopefully. There is a building that I see very frequently in Mahdi that is at a very slight tilt. And it's getting worse, which is kind of scary. And it's like tilting like this, and then the building kind of a little bit beside it over here is where my daughter goes to school. So if it falls, it's going to hit the next building, but it won't fall this way. Yeah, we'll see how it works. What's that?
One of those buildings that are red bricks only?
No, it's not one of the ones that are just red bricks. Like it has coverings on the outside, but I'm sure underneath it's red bricks. Pardon me? No, she's not old enough to be in this school. So my daughter's at Hadana. So she's, yeah. Yes, so she's learning Arabic at the same time as she's doing that. It's all Egyptian teachers. She says some things, but she normally doesn't speak Arabic. So the other day she said something funny. What did she do? Oh, she was taking out like a container of Baby Bell, like you know the cheese that's round. She took out a thing of Baby Bell and then dropped it on the floor, and then she laughed and she's like, Balash. It was quite funny. Okay, so Some of you have seen something like this, a teeter-totter or a seesaw, something you see on the playground where you have two people sitting on the sides and it goes up and down, right? You know what I'm talking about?
Yes.
Okay. So if we consider something like this, where we've got a 100 kilogram student on one end and a 50 kilogram student on the other. So let's draw this. So here's our two students. Yes, I just drew them as boxes. Let's say this is mass 1, which is 100 kilograms. This one over here is mass 2, which is 50. Intuitively, what's going to happen in this case?
100.
The heavier kid's going to fall down, the lighter one's going to go up. Right? You can have a fun time playing this on the playground. You can stay on the bottom, the other kid's stuck in the air. So if we're looking at this, we want to look at what is the net translational forces, meaning what are going to be the forces in the x direction, and what are the forces in the y direction. Well, let's draw this out. So on my object here, I'm going to have force of gravity 1, and we're just going to look at what are the forces on this beam. So on the seesaw, teeter-totter, whatever you call it, itself, what are my forces? So I'm going to have an FG2. Don't worry so much about length of the arrows, this unit. I'm not going to be picky about that. What other force do I got going in this case? I'm not going to deal with normal forces with the students because I just want what are the forces on the beam. Yes. So right here, I have some sort of normal force. Is that what you're referring to? Yeah. So these are the three forces acting on the beam. Yes, technically, the beam is going to have some mass. So there's probably going to be a third force of gravity on this. I'm not going to talk about that just right now. We're just going to look at this. Yeah?
Isn't on mass 2, there's a force that's going upwards?
Yes, there is. There's a normal force on M2. There's a normal force on M1.
I'm not talking about normal force. Because 100 kilos is heavier, it's going to be like this.
Mm-hmm.
So this one, there's a force going upwards.
I get what you're saying. So you mean after this tilts,
Yes, so
this one's stuck on the ground and this one's up in the air?
and the force is determined by the FG1. The heavier it is, the more force it has.
So you're correct, but we're going to look at this before it moves.
Okay.
So we're not going to talk about it moving yet. We're just going to keep it at this. So we need to look at what are the net translational forces in this. I need to quickly open up my set of notes here because I forget what I put in these blanks. And I don't want to teach you this wrong. Because that would not be great. All right, so because in this system, have you ever seen a seesaw fly into the air? Nope. Have you ever seen it fall into the ground? Have you seen it shift left or right? So what does that tell me about the x and y forces? They're in equilibrium. So the net translational forces in the x direction, so we would say the sum of the forces in the x direction equals 0. Same thing, sum of the forces in the y direction equals 0. But is this system going to move? Yeah, we've already established that, right? It's going to rotate. So what we talked about in the first section with translational forces, this tells us nothing about rotation. Like this rotating. So what I've got with this is this must mean the normal force going up is going to equal these two FGs. So we know that. But nothing about this tells us that we're going to rotate. And this is not something you've seen before. So that's what we're going to get into in today's class. Mm-hmm. Yes, but again, you're thinking of after this system has moved. Our system hasn't moved yet. So at this point, when the beam is like this, what's the forces acting on the beam are the two FGs are pulling straight down, and the normal force is going up. And because we know that on this beam it's not going to move up or down, those forces have to be balanced. This is just dealing with Newton's laws, all of them together. So this system is not going to accelerate up or down. So those forces have to be balanced, because otherwise we're going to have some sort of acceleration.
I was going to say that it's the same concept when you draw your body diagram and
Mm-hmm.
whether it's accelerating or not.
Yeah, exactly. Now, the reason why this is so much different than dynamics is because look at where my forces are. Everything we've dealt with dynamics, we dealt with one object, and all the forces started from the center of that object. But notice here, my forces are not starting at the same point. This is what causes rotation. And this is what we need to consider with this. So even though we've got net translational forces are 0, this one has a net torque. And I'll explain what torque is in a sec. So, because of this, we're not actually in equilibrium. Again, equilibrium means everything is not moving. We don't want a rotation, we don't want something like that. So, for an object to be in equilibrium, they both have to have translational, and we need to have rotational equilibrium. So translational equilibrium means we're not moving up and down, left and right, and we're not rotating. Is it the same as what, sorry? Dynamic equilibrium means that we are moving, but it's in equilibrium, which is still slightly different than this. So if something is not in if something is not in rotational equilibrium, it means you're going to have some rotation. So torque, this is our new concept. This is the only thing that's going to be different from last unit. So basically what torque is this is causing some sort of rotation on an object. So our definition of this, or our equation, is the Greek letter tau, which kind of looks like a T, just a squiggle, and then a backwards J basically. This is equal to force times a distance. And this distance is the distance to your pivot point. I'll explain what that means in a sec. And the unit for this, we can just look at the equation. Force is a Newton times distance, which is meters. So torque is Newton meters. So in order to picture what I'm going to do with this, we need to talk about what do I mean by distance to pivot. So if I take my binder here. So here's the top of my binder. I can cause this to rotate, right? So the amount of force and the amount of pivot I need to apply on this depends on how far away from the center I'm pushing. So if I push outwards here, it's pretty easy. Whereas if I had to push closer to the center, it's harder to push that open. I've got another good example of this, but I need to go mobile for a sec. This is going to be slightly weird for everyone who's watching online. We're going on field trip to the other side of the room. So, think about a door, right? Everyone's used a door before. Any guesses why with a door, the handle is on the outside? Maximize distance. Why does that make a difference? Easier to open the door. So let's think about this. If this is my door, if I'm pushing on this side of the door, it's pretty easy to open and close it. Right? What happens if I push way over here? You have to push a lot harder to close that door. Whereas if I apply the same amount of force here, easy. Does that make sense? So if I look at the equation for torque, torque is the amount of force times the distance from my pivot point. And this has a set pivot point. So the further the distance here, the more pivot I'm going to get, or the more amount of rotation I'm going to get from that. Does that make sense? Yeah, so the D is just what is the distance from here to here. So it doesn't matter about the rotation distance because in equilibrium we don't want rotation, right? So it's not looking at a circle and what's the circle it rotates. It's just what's the distance from the pivot point that I'm going to do with this. Because it all depends on how far from the pivot it is. So intuitively, so here's my pivot point. The hinge is on the door. So the further away from this I push, the easier it is to close that door. And that's why you've got handles on this side. Because it's pretty easy to open and close. And my squeaky door. Whereas if you put the door handle here, and you try and open and close it, it's going to be a lot more difficult. Another concept I want to talk about, I'm not at it yet, but I'm going to, is thinking about this door. What happens now if I push this way? I'm not applying torque, but I'm applying a force, and I'm at a distance. Why does this not work? Yeah, this. If I push into the door like this, does it cause rotation? It's not the right direction, right? So you would need to push perpendicular to the door as opposed to parallel to the door. Does that make sense? So that's going to be more tomorrow's class, but I wanted to show that now just while I'm here. Any other questions with this? No? All right. Why? Because you can finally lean back against the desk so it's a little bit comfier. All right, so that's where this distance to pivot is. It just means what's the distance from your pivot point to where that force is being applied. So let's try a question on this. Really simple one first. So any of you changed a tire before in a car?
Me.
A few people. How big is the wrench or the tire iron that you use in order to loosen off those lug nuts? 30 centimeters. Yeah, it's ruler size, or some people, I've seen some crazy long ones. And this concept is why you've got longer wrenches to pull this, right? So if you don't know what a lug nut is, if you have your tire, it's got these, normally it's around 5 little lug nuts on it to hold the wheel on. You want those things to be pretty tight. Otherwise the wheel's going to fall off your car. So in order to apply the most torque, in order to do this, yeah. But you're applying a force a farther distance away from your pivot point. So if your tire's here, here's the lug nut. If you want to loosen this, you don't have some little wrench and you try and go like this, you're not going to get it off. The longer the wrench, the easier it is to twist it. So if we're going to do this,
But isn't this just because you get more hand space to like push?
so it's not just about the hand space, it's about the torque. Because in order to twist something, you need enough torque to get it. So that's why if you just take your hands and try and twist it off, it's not going to work. Your distance is really close to where the rotation is. That's why you've got a longer object, then it's a lot easier to twist it off.
Going back to cars, like you said in the beginning of class, that if you want more torque, would you have more longer, bigger tires? Yes.
Bigger tires do give you more torque, yeah. Mass is not a part of this, no. But if you think about it, what happens is your car is able to apply a certain amount of torque on the wheels because it all starts with the rotation of the axles to get your car spinning, right? So your car can apply a certain amount of torque onto the tires. Depending on how long your tires are, it can apply a greater or lesser amount of force onto the road.
Same thing with the gears.
Pardon me?
Same thing with the gears.
With the gears, yeah. Yeah, gears is a little bit, it has to do with this. Because depending on the size of the gear, again, same amount of, or it changes the amount of rotation you can have. It's all using this logic. So if we need this amount of torque, so 24 Newton meters is needed in order to tighten one of these lug nuts. If you can apply a force of 100 newtons, what's the minimum length of the wrench that is required for this? So we have the equation, we can just solve this. Torque equals force times distance. We have the torque, we have the force. So the distance is going to be 0.24 meters or 24 centimeters. So if you happen to be not the greatest at strength, in order to loosen up something, what's the easiest way for you to overcome your lack of strength? Longer wrench. You can compensate for that strength.
And when is time going to be a factor?
Time doesn't have a factor with torque. Because it's just in...
How long would I have to apply 100 newtons of force for something, or in this case for...
So then you'd have to talk about how many degrees are you wanting to rotate it, and we're going to get into circular motion later. But it's kind of on the right track. So in order to talk about this, we need to deal with a few more things. First of all, we need to talk about if torque is a vector or a scalar. What do you think? Vector? So, doesn't matter what direction my torque is applied.
No.
You sure?
Oh no, perpendicular.
Sure does. How many of you have tried to unscrew something or to tighten something and you're twisting it the wrong way? Does it make a difference?
Yeah, I broke it.
There you go. It does make a difference.
That's the...
You're just too strong. Torque is a vector. You either apply clockwise torque or counterclockwise. So it doesn't matter. It even says here. Yeah. I will get to talking about the directions in a sec. I'll get to that. So if an object is in rotational equilibrium, what can you tell me about the sum of all the torques? They have to be zero. So not that they're equal. I think what you mean by equal is saying that torque clockwise equals torque counterclockwise. So we have this, or we can write it out as torque clockwise is equal to torque Counterclockwise. I have a story about clockwise and counterclockwise torque that I don't want to put up on YouTube. So remind me at the end of the video to tell you about it. You'll find out once I say it. Now everyone online is going to be curious about what that is.
We're gonna ask you some more.
Yep. Nope, I'm not going to put this one up. Okay, so what's going to happen is we need to now talk about 3 different items, because these are going to be important in dealing with torque. So first of all, center of gravity. What's center of gravity?
Where you can draw FG where all the force of gravity meet, like if someone's heavy on the right side, so the gravity will be on the right.
Yeah, so it talks about the density of an object and where can I apply the force of gravity. So if I've got a long beam, the force of gravity is essentially acting at the very center of it, if it's an equal density. So the center of gravity is where the force of gravity applies.
So where there's a balance in mass?
So it's essentially yes. Yeah. It's like if you take the average of all the masses of all the particles in an object, it's where the very center of that would be. Yeah. So this is technically not the definition of it, but this is what you need to know about it.
In this case, is it
No, it's not going to be a pivot point. The center of gravity is sometimes it's the pivot point, sometimes not. Uniform beam just means your beam, the bar, whatever we're dealing with, is uniform in its density, meaning that every chunk, if it's the same length of the beam, has the exact same mass. So this just means constant shape and density. So this helps us in figuring out where the center of gravity of an object is. If it's a uniform beam, the center of gravity is in the middle. Pretty easy. Arbitrary position of rotation. So this one, if you know what each of those terms mean, it's not too bad to remember it. Arbitrary just means it doesn't matter what you pick. So if I was a very cruel teacher and I said, all my students are arbitrary.
If you include that.
If I would say that.
We were called that every day for like a year.
You were arbitrary?
You're so arbitrary, guys.
Oh.
We once had to do an essay about fiber.
We know the word well.
As a part of.
So this brings up dread in your in your soul when I say the word arbitrary. So what does arbitrary mean?
It's like those model system where it's like.
No, like to do something without reason.
Yeah, something else.
more like a punishment?
No. So
You say something and you
No, that's
that's contradictory or hypocrite.
don't.
So arbitrary and what we're going to be. So arbitrary means it doesn't really matter. In the context that I'm talking about. I don't know what your other teacher was talking about. In this, so arbitrary position of rotation means where I pick my rotation doesn't matter because it doesn't make a difference if I put it here or here. If you want the actual definition of arbitrary, you can look that up. I'm not going to say anything about a previous teacher and say if what my definition of arbitrary for this is the same that they use. So arbitrary position of rotation just means you pick the pivot point. Okay, so these three things are very important when we talk about torque and rotation. Just based on center of gravity makes a difference, I need to know where to put Fg. Uniform beam tells me where that center of gravity is. Arbitrary position point, I will show you examples of where that is. So let's do our first actual rotation question. All right, so what we've got here, we've got a store sign. Jen and Eric have a store, and they want to hang it from this beam. It doesn't work. I've stopped trying to fix those. I don't know if squeezing it works this time. So with this, we are told that this pole has negligible mass. Anytime you hear negligible, that just means the mass is so small we're not going to use it. Yes, it's vinegar, because vinegar kills bacteria.
We're testing if I can smell.
Good. I'm glad you haven't lost your sense of smell.
Are being ruined. I'm getting like these tears.
Yes. You know what a hypochondriac is?
No.
A person who hears about some sort of sickness or disease and they immediately start thinking they have it.
And then I search Google and I find the symptoms and then I relate to the symptoms and then I think I have disease.
Yeah, exactly. The problem with COVID is everything's a symptom, basically. I don't know. I don't know if optimistic would be a good one for that. How did I get onto that? I have no idea how to get on that topic. Okay, anyways, we've got a sign that's hanging from the pole here. We want to know what is the tension here in the rope. So your strategy with this is going to be similar as to what I showed yesterday. We need to start by drawing all the forces that are acting in this situation. So if I'm looking at the beam, because I want to know what are the forces acting on the beam. So here, this should be there. We've got tension that's acting on the end here. I've got a force of gravity due to the sign. We're told the beam does not have a mass, so we're going to not put an Fg. And that's it, I think. There are forces acting on the hinge, but I'm going to show you why we're going to ignore that. So there's tension here, which is holding onto the mass, but because the tension and the force of gravity have to be equal, I'm just going to simplify it and say this is Fg. Technically, yes, you're correct, but I'm going to oversimplify that. So in order to figure this out, we need to look at balancing these torques. So I need to know that my torque clockwise is equal to the torque counterclockwise. And what I'm going to do, because I can pick any pivot point, I'm going to pick smartly. I'm going to pick this as my pivot point. Now, why would I pick that as my pivot point? Well, there has to be some forces on this pivot point. If there was not any forces here, what would happen to my sign? It would fall. So there must be some force upwards here. But I don't know what that is. So if I pick this as my pivot point, what is the torque by the force upwards at that point? 0. Why? Because my distance, if you remember our equation way up here, torque is force times distance. The force here is at a distance of 0. So even though my position of rotation is arbitrary, I can pick it smartly so that I cancel out the forces at that point. If what, sorry? If it doesn't have a distance, what would be the opposite force? You can't have a torque with no distance. It's impossible. We don't. We have a force, we don't have a torque.
You can just use what the
Like, force production, normal force, force opposite force.
There is no opposite force of torque. It's just torque or torque.
So we don't draw it onto that.
Right now we're not. And I think there's a later question that talks about how to get that force. But right now we're going to ignore it. So for this, which of these forces is causing a clockwise rotation? So what you might want to do with this, and on your test and on your paper, you might want to put your pen on your position on the beam, put your fingers at the pivot point, and check this out. So if I wanted my pen to rotate clockwise, I would need a downwards force. So therefore the Fg is going to be my clockwise force. So it's going to be force of gravity times distance, I'm going to call this distance 1. So just what is the distance to that point? And this is equal to, the tension is causing an upwards force. So if I have my pen, tension requires an upwards force, which gives me counterclockwise. So this is going to be tension times, let's just call it D2, which is this distance here. From here, we can now solve this. I have everything I need. Are we told the newtons of the sine? Perfect. So I don't even need to calculate that. Distance to that point, so here's my pivot. Distance to this force is 1.3 equals tension, which is what I'm looking for. And the distance to my tension force from the pivot point is 2. So from here you can calculate it. I found my set of notes, so I'm just going to look at that. With this unit, I don't care about direction in your questions. It'll be important when you set up your diagram, but notice I already indicated direction here. So we already know this. Same with free body diagrams. I didn't ask for you to tell me direction because you already showed it in the free body diagram. Because we want distance to the pivot point. So if my tension acts here, my pivot point is over here. So that's why I picked that as my distance. You're told this in the question.
It's normally will be equal to both the tension, both cables.
Well, the force by the wall plus the tension would equal Fg, yes. We're going to get there.
Then why don't we ask for
Because I picked this as my pivot point. And as we saw, so if I were to go back to the door example, if I looked at the pivot point on the door, if I pushed on the hinge, is the door going to move? No. So this force up on the wall, or by the wall, at the pivot point doesn't cause any rotation. So that's why if this is my pivot point, I just ignore it. I forget if the next question asks about that force. Yeah, it does. So extending this question, so if I just quickly redraw this. So here's my system. We want to know the horizontal and vertical components of the forces here. So we already established, we know there must be some force in the y direction. It's asking what's this, and what's my force in the x direction. We already have, this is Fg. We already have, this is tension. And we want to know these other two forces. So in order to solve this, there's two things we could do. One of them is much easier. One of the ways we could do it is we could pick a different rotation position. So I could say instead of this being my pivot point, let's pick over here. Then I can ignore tension, because that's at distance 0. And I can base my distances from that pivot position. That takes extra time. That's not what I want to do. You can do it. It just isn't helpful. What's a better thing to do is looking at my forces up equal to forces down, and my forces left must equal to forces right. And this is just from yesterday. This system is not accelerating up or down, so those forces have to be balanced. My system's not accelerating left and right, so those have to be balanced. And then we can just go about solving this. So my force is up. If I look on my diagram, I've got force in the y direction that I said here at the pivot point, plus tension, equals the force down, which is Fg. Any concerns with that? This part should be pretty good. Okay, so that means Fy is equal to Fg, just 350, minus tension when I bring it to the other side. What did we say tension was? 227.5. And you get your y component, which is 112. It's rounded. Should be 112.5. There's the y component. Let's do the x. So I just assumed the x was to the left. Okay? I could have assumed the y was down. And then when I would have done my equation, I would have gotten a negative answer. That just means I picked the wrong direction. So intuitively, we thought this through and said, if there's no force here, what direction does the beam go?
Down.
It would go down, right? If I've got a rope holding this side of the beam, something pulling down here, this side of the beam is going to go down. So the force must oppose that motion, which means it's pulling up. That's how I just intuitively figured this out. But if you guessed it wrong, don't worry, you'll just get a negative answer. For the x, so I picked this. I said it's going left. But notice here, what are the forces going to the right? Nothing. There's no x component. So that's it. So the wall does not pull the beam into the wall.
What is the wall?
Why is the y component upwards?
No, why is the wall upwards? Why is it not towards the wall?
Because the beam is attached to the wall. There's a hinge that's screwed into the wall, and that's what's causing it to be there.
It's just like force pulls hanging up.
Yeah. Yeah.
Can I go to the door?
Yeah. Any other questions with this?
I thought like the X component. What like something like force deflection maybe? Or something going. What kind of thing is
So, most cases like this, what's going to cause your forces on the wall is going to be your hinges actually screwed into the wall. So sometimes at that position, it's going to have an X component holding it sideways. Sometimes it's just a vertical position. So just like we're not considering how is the rope attached to the beam, we don't really care how the beam is attached to the wall. How they're attached is irrelevant. We just need to know there's a force acting on it at that point.
And if we were to like draw up the errors differently, would we say that applies downward from this like top?
Mhm.
So if you use any
So-
combination you want.
Yeah, so if I said Fy is down, then I would have tension equals Fg plus Fy, and I would just get a minus here, which means it's not down, it's the other way. It should be up.
Always have to be like some components positive and other negative, or can be like can X keep on going to the left, but Y is down on this thing in a different diagram.
Yeah, yeah,
So it doesn't
yeah.
matter.
Fy won't always be up. It could also be down at some points as well. Which cable?
The one holding the sign.
Yeah, as we established, this tension on this cable is just equal to the force of gravity on the sign.
So shouldn't it be in the equation?
No. I canceled it out and I substituted it with Fy, or sorry, with Fg. Because otherwise you're just making it more complicated. Then you're saying, then at this point I've got Fg down this way, I've got another tension going up here, but tensions are the same, so the tension pulling down here is the same tension, and that has to equal this one. So instead of writing all this, it's way easier just to say the tension here is the same as force of gravity.
Because the tension has the upward and downward tension.
Yeah. Yeah. There's still something there. There we go. Yeah.
Again, the Phys will be like a clockwise force.
No, because my beam's not here. It has to be along the beam. Yeah. Because my wall's not going to rotate.
And if you got negative numbers, we just put it as negative numbers.
So then you would have to, if you got a negative answer, go back and switch your, so keep this as negative, or show this as going down, keep it as negative here, and then underneath just say 112.5 newtons up. So just indicate you recognize you had the wrong direction. Don't go back and change everything, just go with that.
What the downward tension of the other cable?
What about the what?
The downward tension of the other cable. Like the one on top.
That the tension down here is acting on the wall, not on the beam. Or on the seating. All right, let's move on, because we spent a lot of time on this question. Yep. I've got 2 more to go. And you said the other class asked a lot of questions. So I've got 2 students sitting on either sides of a teeter-totter. Notice in this case, you're told what the mass of the teeter-totter is. We're given, what does it say? Student 1 is a mass of 65 kilograms. Sit at the very end of the teeter-totter. You're told the mass of the second student. How far from the pivot point should he sit in order to be in equilibrium? Okay, this is a fun one. So we've got a 65 kilogram student sitting at the very edge. Here we go. FG1. Well, it depends on how old these kids are. So there's our first kid. We're told student 2 has a mass, but we don't know the distance that they are. So let's put them, I don't know, let's put them here. So this ones are 90 kilogram. This ones are 65. What other forces we got? Normal force in the dead center. Does it say uniform? No, we're going to assume it though. So we got a normal force. What else?
Is that normal force equal to both of these?
No.
This is equal to 800 plus 9 kilograms.
No. So you're dealing with masses, not weight. So we're also told that teeter-totter has a mass. So I need to include here another FG3. Technically, if you want to be fairly correct, this is what the normal force should look like. But like I said, length I'm not being super picky about, but the normal force needs to equal all 3 of these forces added up. So what are we looking for in this question? Yeah, so I want to know from here to here, what is this distance? Let's call this distance 2 to match with FG2. So that's distance 2. Where is, well, here's distance 1. What is this distance? 1.3. How did you get 1.3? So I want from FG1 to the pivot point. I'm going to have this as my pivot point. This is an obvious choice. So This is my distance, so it must be 1.3. What is my distance to FG3? Nope. FG3, what's the distance to FG3? 0. What's the distance to FN? 0. Great, so I don't care about those forces. Even though you're given them, I don't really care about them. So if I want to know pivot point, let's look at torque clockwise equals torque counterclockwise. What is my clockwise force in this case? FG2. So if I were to put my pen at the pivot point, this force causes clockwise rotation. This force, counterclockwise. So when in doubt, use your pen or pencil, whatever you got. So clockwise, this is FG2 times D2. Again, that's the torque based on this force. And counterclockwise, we said already, is FG1 D1. Now we can solve it. We're good. FG2, we're told the mass is 90. Do not forget to turn this into a force. In this case, yes, but I'm not going to just yet because I don't want you to forget about them. But yes, you're absolutely right. So 65 times 9.8 times D1 we said is 1.3. Solve for D2. Should be able to do this no problem. 0.94. If I asked you what is the normal force, how would you go about doing that? Add all three FGs. Yep, because forces up equal forces down. So, and I know FG1, FG2, FG3. Good. So I don't need to show you that. Yep.
Well, what is D2 different than D1?
Because they're not the same distance from the pivot point. And if you think about it, the two masses are different, so the two forces are different. If they were at the same distance, the 90 kilogram student would go down and the 65 would go up. So this would be like if you're on the seesaw, sitting in the middle. So not actually sitting on the seat, you could sit in the middle. If we had a seesaw here, we could actually test it out and try it. But we don't. Yeah.
So I get that clockwise part, but that is going down.
Mm-hmm.
But why, or why is FG1 still like the clockwise? Is FG1 also going down?
So they are both going down, but because my pivot point's here in the center, going down here gives different rotation than going down here.
Oh, so like when we're going clockwise, that way.
So this is clockwise, counterclockwise.
Oh, so when you try, it turns out that they technically both go down.
Yeah. So even though both forces are going down, they cause different rotations. Is this my last question? If you switch to the next page, is it? Nope.
If you want to add more questions to the video,
You want this video to be as long as possible. You guys are so cruel. So this is let me understand your logic in trying to make this video longer to make the other class have to watch a longer video. So by you doing this, you're making this video longer so that the other class has a long video, which they in turn, when they watch that, they're going to think, oh, I have to watch a really long video. Therefore, I'm going to ask less questions to make the other class have a lesser video. Do you think that's going to happen? Or are they going to think, I don't like the other half of the class because they make our videos long. So what am I going to do in turn? I'm going to make yours longer. So the only way to, if you treat someone terribly, In general, they're not going to treat you kind back.
Yes, exactly.
What we're doing right now, what we're doing right now is a response. It's not the beginning. We started with the 55.
Yes, 50 minutes.
We're not responding with an hour.
Twice in 1 minute. It shouldn't be longer than 20. What a truth.
Last minute, we gave our meeting 25 minutes long.
How long is it?
They gave us 50 and 55 minutes long. We're now responding to the response.
Let's do the last question. Then you can stop complaining. I'm going to do this one with no questions. I'm going to solve it straight without any interaction with you. How about that? All right. So this should look very familiar for someone who wants to build a bridge. If you're going to do engineering, civil engineering, this might be your life. So what you're going to want to consider is how much do you want each of these posts to support? You'll need to think about this. As your truck is driving across the bridge, you want to make sure it can support the truck through the entire trip. So in order to start this, I'm going to look at all the forces acting on this beam. The bridge, the part that's being suspended. So what I've got is I've got 1, 2, 3, 4 forces? Yes, 4 forces. So we've got, this bridge obviously has some sort of mass. So let's do FGB for the bridge. I've got the truck is at this point. We're told it's 5 meters from this support. Let's call this FGT for truck. Then also on this beam, I've got 2 supports. I've got one on here. I'm just going to call this FL, force for the left side. And I'm going to call over here force right, because it's on the right. You could call it force 1, force 2. You could call it whatever you want. I could care less. Just label it. If you call this F for force, this for force, you're going to get confused. Next thing I want to look at is a torque equation, a balanced torque equation. So I've got torque clockwise equals the torque counterclockwise. So because I can pick any pivot point at arbitrary, I want to be smart about this. So I've got 2 unknown values. I don't know force left, I don't know force right. So you need to be strategic so that I can figure out at least one of these. So let's pick this as my pivot point. You could pick this one. You'd solve for force right first. Doesn't matter. I chose this because you're given this distance from there. So why not make your life a little bit easier? So from this, I need to figure out clockwise force. So again, using my fancy pen trick, hold the pen on this end, pushing up gives me clockwise. So FL needs to be clockwise. The 2 FGs are pushing down, counterclockwise. That's my strategy with that. So force clockwise, we've got FL times the distance to this. So I'm just going to label them all the same to indicate that the distances match with the forces. So in this case, DL, boys, shh. For this case, 15 meters is my DL, because that's from the pivot point to the force. Then I'm going to do counterclockwise. So we've got force of gravity based on the bridge times distance to that force of gravity plus FGT, so force of gravity to the truck times the distance to the truck. Again, I just use the same subscripts so that you know that those are paired. If I'm looking at those distances, so to FGB, to my pivot point, this is going to be DB, distance to the center of the bridge. I don't think it said uniform. We're going to assume uniform unless it tells us otherwise. So it's halfway there. So this is 7.5 meters. And then this distance here is distance from the pivot point to the truck. So that's why I picked this smartly. And from here, it's just a matter of plugging in numbers and solving it. So FL is what we're looking for. Distance to that is 15. FGB, we're told, we're told the mass, so we need to do 6500 times 9.8, which is the acceleration due to gravity, times the distance, 7.5, plus, I'm going to go down here, truck, we're told the mass, 3,500, 9.8, times the distance, 5. So notice, this is why I did not just cancel out G on the last example. It won't always cancel. So I wanted to show you the whole thing. If you put it in and you realize, oh, these can cancel, please do. It'll make your life easier, but put it in first. Plug this all in. 43,300 newtons. Someone please double check that. Did I write the right one down? Okay, so it worked. That's a great question. Is the left force equal to the right force? Are my forces balanced and equal throughout the whole thing? No. So therefore, they're not going to be. So there's two ways, again, we could solve this. You seen, Danny? Shh. Just don't tell me anything. Then, I can either pick this now as my pivot point. Do the same thing. That requires a little bit more math, so why not make it easier? Forces up equal forces down. Both will get you the same thing. One of them is a little bit lazier. So forces up, forces down. And from here, it's pretty easy. So the forces up is just force left plus force right. Forces down, FGB plus FGT. So, so FR is just this plus this minus this. And because I don't want to write all those out, we've already solved for all these, I'm just going to write the answer. Because you guys are brilliant enough, I don't need to put in numbers. So this is how you go about solving this. So you're going to use a combination of strategies. There is net torque equation equals 0. There's net force equations equals 0. So I can balance that with forces up, forces down. If you want to speculate for tomorrow's class, I only used forces up, forces down. Tomorrow incorporate forces left, forces right. These forces are very nicely 90 degrees to my beam. Tomorrow they're not. We're going to have forces at an angle, which means we need to have parallel to the beam components, perpendicular to the beam components. It is easy. Just take this, add triangles. So easy. Okay. So I'm going to answer questions now. So those of you watching online, you're more than welcome to stop at this point because it's an hour and 3 minutes long. Pivot points on the right. This is not clockwise. Pushing down is not clockwise. I am considering rotation. Since when does the clock rotate this way? So what if this was a clock, what direction would the hand turn? If this was a clock, what direction should it rotate? Which direction should it rotate if this is a clock? This clock will go like this. Right? So what force causes this to go up? This one. Yeah. So FL is going to cause clockwise rotation. These other two cause your clock to go backwards.